Imagine you could press pause, not on a video, not on a podcast, on the world itself. Everything around you simply stops. You're standing in the middle of a busy street, and every car is frozen mid-turn. A dog is suspended in the air, mid-leap. Coffee is falling from a tipped cup, hanging there, each drop a perfect amber lens. Then you press play, but slowly, 1,000 times slower than normal, 10,000 times, 1,000,000. What would you see? This question seems like the setup to a science fiction story, but physics has actually answered it. Not by slowing the world down, but by building instruments sensitive enough to catch what happens at speeds the eye will never reach. And what those instruments have found is that time has layers like geological strata, one beneath the other, each one hiding a world the one above it never suspects exists. Today we're going to peel those layers back. We start with a single second, something so ordinary you've already used dozens of them without noticing. And we're going to descend, step by step, into timescales so small they have no name in everyday language, a journey not forward in time, not backward, but inward, into the hidden architecture of the instant. Let's begin with the familiar. A second. You know what a second feels like? It's just long enough to say one Mississippi, long enough to decide whether to answer a phone call, to catch something falling from a table. An Olympic sprinter runs roughly 10 meters in a second. A hummingbird beats its wings about 50 times. Your heart, probably once or twice. A second is the unit of time that human civilization built its clocks around, precisely because it fits so naturally inside the human body, inside human experience. But 1/10 of a second? That's already getting interesting. If you've ever watched a batter face a fastball, you've seen the edge of human reaction time. From the moment the ball leaves the pitcher's hand to the moment it crosses the plate takes roughly 4/10 of a second. The batter has about 2 of those tenths to decide to swing, and another 2 to actually do it. 1/10 of a second is the frontier of conscious decision-making. Below it, you're no longer thinking. You're just a collection of trained reflexes firing in sequence. 100th of a second. The gap between first and second place in an Olympic sprint finish. You don't perceive 100th of a second as a unit of time. You perceive it as very fast, and then it's already gone. But events that unfold in hundredths of seconds are everywhere around us. Completely invisible, completely ordinary, completely unexamined. 1,000th of a second, a millisecond. You'd think nothing interesting happens in a millisecond. You'd be wrong. Here's a question nobody thinks to ask when you bounce a tennis ball off a wall. How long does the bounce actually take? The whole thing looks instantaneous. Ball hits wall, ball leaves wall, but the ball doesn't pass through the wall. It has to compress, stop, uncompress, and launch itself back. That process takes time. How much? You don't need a physics degree to answer this. You need one formula, the simplest one in all of mechanics. Distance equals speed multiplied by time. Rearrange it. Time equals distance divided by speed. A tennis ball hit hard travels at maybe 15 or 20 meters per second. When it hits the wall, it squashes by maybe a centimeter or 2. Let's call it a couple of centimeters. Divide that distance by that speed, and you get a few thousandths of a second, a few milliseconds. An event that looks instantaneous contains several of them. A ping-pong ball hits harder, compresses less, bounces faster. Chinese researchers, who care about these things professionally, measured it at about half a millisecond. These are not unusual phenomena. These are Tuesday. Now go stand in any room with LED lighting and look carefully. Not at the lights directly, just notice the space. Many LEDs don't shine continuously. They pulse. They flicker at frequencies your eye smooths over into steady light the way a film's 24 frames per second look like motion. But the flicker is there. If you take a photo while slowly moving your camera sideways, a flickering light will leave a dotted trail. and a steady one won't. Try it tonight with your phone pointed at any LED indicator or any appliance. The dots tell you how fast it blinks. Most household LEDs pulse somewhere between 100 and a few hundred times per second. This is a physical phenomenon happening around you right now. You've been ignoring it your whole life, but you don't even need a camera. A little practice is all it takes. If you move your gaze quickly across a flickering light, not your head, just your eyes, quick sideways, you'll start to see the strobing. With some training, human observers have detected flicker frequencies above 3,000 hertz, 3,000 pulses per second. Your visual system is slower than that, but not by as much as you'd think. Go deeper now. A microsecond, 1/1,000,000th of a second. A supersonic bullet travels roughly a kilometer per second. In 1 microsecond, it moves 1 millimeter. That's slower than a snail. If you could freeze time down to the microsecond scale, the most violent projectile in everyday experience would be barely creeping. Everything macroscopic, everything you could hold or throw or drive would be effectively still. But cracks are not still. When a hammer hits glass, the fracture doesn't just appear. It runs. Cracks propagate through glass at speeds measured in hundreds of meters per second because a crack is not moving matter. It's moving a failure condition through a crystal lattice. The sound of breaking glass is slow. The breaking itself is not. A crack racing across a window pane does so at roughly the speed of sound in glass, faster than any bullet. And it does it in microseconds, filmed at 100,000 frames per second. A shattering windshield looks like a zipper being pulled. Neat, sequential, a front of destruction racing from point of impact to the edges. This is what violence actually looks like when you have time to watch it. Here's a simpler example. Take a dry spaghetti noodle and bend it. Don't snap it, just apply gentle, even pressure, and let it break on its own. Watch what happens. It almost never breaks into two pieces. It breaks into 3, 4, sometimes more. This puzzled physicists for a long time. If you apply force evenly to both ends, shouldn't the stress be uniform? Why multiple breaks? The answer lives in the microsecond timescale. The moment the spaghetti breaks, it doesn't immediately relax. It springs back. A rebound wave travels through the pasta at the speed of elastic stress waves in that material, hundreds of meters per second. That rebound reaches the already stressed sections in tens of microseconds and snaps them too. The whole cascade, every break, happens inside 1 millisecond. The spaghetti breaks itself. You just started it. To actually see this in detail, you need a camera capable of tens of thousands of frames per second. Researchers have filmed it. The breaks don't happen simultaneously. They're sequential, one following the other with gaps of about 35 microseconds between them. 1/30,000th of a second. Completely invisible. The spaghetti looks like it just explodes. What it actually does is cascade step by elegant step in a time too small to witness with unaided eyes. Microseconds to nanoseconds, a billionth of a second. This is where physics meets your everyday internet connection. Light travels 300,000 kilometers every second. Put it another way, 1/3 of a meter per nanosecond, less than a foot. If you could slow time by a billion, you could stand in a room and watch a beam of light creep across it, moving about a foot every heartbeat. This sounds abstract. It isn't. The time it takes a signal to travel from your router to your phone and back is measured in nanoseconds. When a computer engineer talks about latency, the delay between sending a request and getting a response, they're counting nanoseconds. The cables inside every computer are length-matched precisely so that signals from different parts of the circuit arrive simultaneously, differing by nanoseconds at most. The entire architecture of digital electronics is built around managing time at the nanosecond level. And there's a subtler connection. Every wireless transmission, radio, Wi-Fi, cellular, works by modulating an electromagnetic wave. Encoding one bit of information requires at least a few oscillation cycles of that wave. If your carrier wave oscillates 1,000,000 times a second, you can encode something like 100,000 bits per second. That was early radio. Adequate for Morse code, barely adequate for voice. To stream video to your phone, you need hundreds of millions of bits per second. That means your router needs to oscillate at billions of cycles per second, gigahertz. Standard Wi-Fi runs at 2.4 or 5 gigahertz. Those oscillations happen in fractions of a nanosecond. Every time you load a web page, your router is executing billions of electromagnetic oscillations per second. Each one a precisely timed event at the nanosecond scale, coordinating with your device's antenna in a handshake that repeats continuously while you scroll. 5G networks push into higher frequencies still. 6G research, which is already underway, aims at tens of gigahertz and beyond. Higher frequencies, shorter periods, more information per second. The progression is not a coincidence, it's physics. The faster your signal oscillates, the more data it can carry, and the shorter the periods involved, the closer you push to the nanosecond boundary. Descend now into picoseconds, 1/1,000,000th of a second. At this scale, molecules stop. Not metaphorically, a water molecule moves through liquid at speeds of a few hundred meters per second. In 1 picosecond, it travels perhaps a fraction of its own diameter. In 1 nanosecond, it's moved enough to have genuinely gone somewhere. The picosecond timescale sits exactly at the boundary between the world of moving matter and the world of things vibrating in place. Below a picosecond, you can no longer meaningfully say a molecule has moved, it has only vibrated. But vibration is not nothing. Molecules are not rigid. The atoms within them are connected by bonds that act like springs. Stretch them and they pull back, compress them and they push out. At room temperature, a typical molecular bond vibrates at a frequency corresponding to tens of femtoseconds, which means it completes one oscillation in about 30 to 100 picoseconds, depending on what it's made of. Drop below that time scale and even the vibrations freeze, except for one thing. Electrons. Electrons are perhaps 4,000 times lighter than a proton. Because they're lighter, for the same energy, they move faster, much faster. While atoms are barely twitching at the picosecond scale, electrons are racing around inside atoms and molecules at speeds corresponding to time intervals, shorter by several orders of magnitude. The electron doesn't care that the atomic nuclei are frozen. It operates on its own schedule, in its own timescale, and that timescale is the femtosecond, femtoseconds, 1/4,000,000th of a second. A femtosecond is to a second as a second is to 32 million years. This ratio is worth sitting with for a moment. If every second since the dawn of the universe were 1 femtosecond, the age of the universe would be about a femtosecond. This is not a small number. This is a number that breaks intuition cleanly like the spaghetti. Yet chemistry happens at the femtosecond scale. Every chemical reaction at its core is an electron negotiation. Two molecules approach each other. Their electron clouds begin to overlap. One electron senses a more favorable arrangement on the other molecule and jumps, or doesn't. The bonds that hold the old molecules together weaken and new ones form. This rearrangement, this negotiation, happens in roughly 100 femtoseconds. Faster reactions don't exist. 100 femtoseconds is the speed of chemistry at the fundamental level. For most of the history of chemistry, nobody could watch this happen. You could tell what went in. You could tell what came out. You could measure the rate at which reactions proceeded in bulk. But the individual act of bond breaking and bond forming was invisible. It happened too fast. Then, in the 1980s and 1990s, Ahmed Zewail figured out how to watch it. His approach was elegant in the way that the best physics always is. You cannot build a camera fast enough to film chemistry happening. The shutter speed you'd need is measured in femtoseconds, and no mechanical shutter can operate that fast. But you can use light itself as your shutter. The idea: generate two extremely short pulses of laser light. The first, the pump pulse, is the trigger. It kicks a specific bond in a molecule, starting the reaction. The second, the probe pulse, arrives a short time later and measures what the molecule is doing right now. How does it measure? By scattering off the molecule and reporting back on what it found, the arrangement of atoms, the distribution of electrons, the state of the reaction at this particular instant. Then you repeat the experiment thousands of times with a slightly different delay each time. When you stack all the probe results in sequence, you build what is effectively a molecular movie, frame by frame, femtosecond by femtosecond. You watch a chemical bond break in real time. For this, Zhou received the 1999 Nobel Prize in Chemistry. He had done something chemists considered technically impossible. He had filmed chemistry happening. The same method, applied to biological molecules, revealed something even more startling. The first step of vision, the very beginning of sight, is a femtosecond event. Here's what happens when light hits your retina. A photon enters the eye, travels through the vitreous fluid, reaches the layer of photoreceptor cells, and strikes a molecule called retinal, embedded in a protein called rhodopsin. The photon is absorbed. In response, in about 200 femtoseconds, retinal changes its shape. Specifically, one particular bond in the retinal molecule twists. This geometric change, this tiny structural flip, is the trigger for everything that follows. Protein conformational changes, ion channel openings, electrical signals racing up the optic nerve. The whole cascade that becomes conscious sight begins with a bond rotation that completes in 200 femtoseconds. Photosynthesis works similarly. The first step, the capture of a photon's energy and its transfer to the reaction center, happens in femtoseconds. The first act of biology, the moment where sunlight becomes food, occurs faster than most people can imagine time existing. This is femtobiology. And it was completely unknown until the tools to see it were built. But femtoseconds have a fundamental limit, and the limit is light itself. Laser pulses are made of light. Light is an oscillating electromagnetic field. The light you can see, the visible spectrum, oscillates at roughly 500 trillion times per second, which means one complete oscillation takes about 2 femtoseconds. You cannot make a laser pulse shorter than a few of its own wavelength cycles. That's not an engineering limitation. That's geometry. Squeeze a wave shorter than its own wavelength, and it stops being that wave. To probe processes faster than femtoseconds, to watch electrons move inside atoms rather than between them, you need a shorter wave. Shorter wavelength means higher frequency, means higher energy. Ultraviolet, far ultraviolet, soft X-ray. But you can't just turn a laser frequency up. You need a fundamentally different approach. Physicists in the 1990s found one, and the method was so counterintuitive that when it worked, the people involved reportedly stared at the results for a while before believing them. It works like this. Take a powerful infrared laser pulse and aim it at a cloud of noble gas atoms, krypton, argon, rubidium. The electric field in that laser pulse is intense enough to temporarily distort the attractive force holding an outer electron to its atom. The electron, feeling this distortion, does something quantum mechanics allows. It tunnels out. It escapes. But only briefly, because the electric field of the laser is oscillating. It reverses direction. The freed electron is pulled back toward the atom it just left. It arrives with considerably more energy than it departed with. And when it slams back into the parent atom, one of two things happens. It scatters, or it recombines. If it recombines, it emits that extra energy as a burst of extreme ultraviolet or soft X-ray light. That emitted burst is extraordinarily short, on the order of 100 attoseconds or less. It happens in a fraction of one optical cycle of the original laser. It's synchronized with the laser pulse because it's caused by the laser pulse, and it carries enough energy to probe the interior of atoms. The process generates not one burst, but a series of them, one per half cycle of the original laser, each at a different harmonic frequency. This is called high harmonic generation. The output looks like a ruler of attosecond pulses, spaced in time, each one a snapshot. With these pulses, physicists can finally film electrons moving inside atoms, watch an atomic orbital rearrange itself after photoexcitation, trace the flow of electrons across a molecule in real time. The attosecond is the electron's native timescale, and physicists now live there, at least experimentally. For this achievement, Pierre Agostini, Ferenc Krauss, and Anne Lhuillier shared the 2023 Nobel Prize in Physics. Lhuillier had observed the harmonic generation in 1987 and spent the following 2 decades developing it into a usable tool. Sometimes the path from discovery to application takes time. In this case, the irony is that it took decades of human time to learn how to manipulate quintillionths of a second. Now we go somewhere few people follow. The attosecond is roughly the timescale of electron motion inside atoms. An electron at the outer edge of a hydrogen atom completes one orbit in the classical picture in about 150 attoseconds. Go deeper into heavier atoms, closer to the nucleus, and the timescales shrink further. Below the attosecond lies the zeptosecond, 1/1000th of a trillionth of a second, 10 to the power of -21. Below that, the octosecond, 10 to the -24. These are not physicists' playful extrapolations. They are measured, studied, confronted. At the zeptosecond scale, atomic electrons have stopped entirely. Nothing molecular moves. The only things that still happen are nuclear events. The nucleus sits at the center of the atom 100,000 times smaller than the atom itself. If you think of the atom as a stadium, the nucleus is a marble on the pitcher's mound. Everything we have discussed so far, molecular vibrations, chemical bonds, electron dynamics, happens in the bleachers. The nucleus just sits there, ancient and dense, watching. But inside the nucleus, there is no stillness. Protons and neutrons are packed together by the strong nuclear force, and they move on timescales set by the size of the nucleus and the speed of nuclear interactions. The traversal time, how long it takes for the influence of a nuclear event to cross from one side of the nucleus to the other, is measured in tens of yoctoseconds. This is approximately the minimum duration of any nuclear reaction. 2 nuclei colliding and fusing do so on this timescale. A very short-lived nuclear state forms and decays within it. Nuclear resonances, the ways in which protons and neutrons can collectively oscillate inside a nucleus, ring at yoctosecond frequencies. But here's something remarkable. Individual nuclear lifetimes can range across an astonishing span. The nucleus of helium-5, a helium atom with 1 extra neutron, falls apart in about 600 yoctoseconds. It barely exists as a nucleus at all before the extra neutron is expelled. But helium-6, with 2 extra neutrons instead of 1, has a half-life of about 0.8 seconds. That is 21 orders of magnitude longer. You could add 1 neutron to a nucleus and extend its lifetime by a factor of 1 billion trillion. Nuclear physics is full of these startling cliffs in lifetime, where tiny changes in composition produce enormous changes in stability. Predicting them requires a full quantum mechanical treatment of how all the protons and neutrons in the nucleus interact with each other, and this is still an active area of research. At yoctosecond timescales, nuclear transitions happen, excited nuclear states, like excited atomic states, but vastly more energetic, can sometimes decay in yoctoseconds, emitting gamma rays. Some of the most violent events in the universe, including neutron-star mergers and core collapse supernovae, are ultimately driven by nuclear transitions happening on these timescales. And then we reach the bottom of what has currently been measured. The fastest process physicists have studied experimentally in any systematic way. Heavy ion collisions at particle accelerators like CERN's Large Hadron Collider or Brookhaven's relativistic heavy ion collider. Physicists take nuclei of heavy elements, gold, lead, uranium, and accelerate them to within a fraction of a percent of the speed of light. Then they smash them into each other head-on. At these velocities, something strange happens. The nuclei flatten. Special relativity compresses them in the direction of travel. From the perspective of the target nucleus, the incoming nucleus looks not like a sphere, but like an infinitely thin pancake, a disk of compressed matter. Two such disks approach each other, overlap, and for an instant interpenetrate. But first, let's talk about what the nuclei actually are at this speed. At rest, a nucleus is a collection of protons and neutrons, each made of 3 quarks. This is the picture from the physics textbook. But a nucleus traveling at 99.99% of the speed of light is a different beast. At near light speeds, the virtual particles that normally exist only transiently inside the proton, the quark-antiquark pairs, the gluons mediating the strong force, become, in a relativistic sense, real. The proton isn't 3 quarks anymore. It's a seething cloud of quarks, antiquarks, and gluons, all frozen into a thin slab by the relativistic compression. This state of matter is called a color glass condensate. Glass because it's frozen, the internal dynamics, slowed by time dilation, can barely change during the collision. Condensate because it behaves like a single coherent quantum system. 2 such slabs collide. They don't stop each other. They pass through each other, or rather, through the ghost of each other, because at these speeds, matter is mostly empty space and strong force fields, and 2 nuclei can overlap, interpenetrate, and continue through each other before the collision effects propagate. In the instant between contact and separation, a structure forms in the space between them, an intense field of gluons connecting the retreating nuclei like strings of color force. This state, existing for fractions of a yoctosecond, has been named the glasma. Not quite a gas, not quite a plasma, not quite the color glass condensate it came from. Something new. A configuration of quantum fields that physics encountered only because someone decided to smash gold atoms together at near light speed. The glasma evolves. The gluon strings stretch, snap, and fragment into free quarks and antiquarks. These thermalize. They scatter off each other so many times so quickly that they reach a kind of equilibrium, a hot, dense gas of free quarks and gluons no longer confined inside protons. This is the quark-gluon plasma, a temperature of a few trillion degrees. A state of matter that hasn't existed since the universe was a microsecond old, now briefly recreated in a few cubic femtometers, lasting perhaps a few dozen yoctoseconds before it expands, cools, and resolidifies into protons, neutrons, pions, and other particles that spray outward and are caught in the detectors surrounding the collision point. Nobody watches this in real time. It's physically impossible. The detectors that surround these collisions are slow by comparison. They're measuring the aftermath, the particles that escape outward after everything has resolved. But the initial events, the glasma, the thermalization, the quark-gluon plasma formation, are reconstructed theoretically by comparing the properties of the outgoing particles with models that assume different things about what happened in the first few yoctoseconds. It's like determining what kind of explosion produced a crater by examining the debris field. You never see the explosion. You infer it from what it leaves behind. This is the bottom of the measured world. Fractions of a yoctosecond, 10 to the minus 25 seconds or less. The fastest physical processes that experimental physics has reached. And it's worth stepping back now to notice the pattern we've traced. Starting at the second, we descended through milliseconds, the time scale of bouncing balls and flickering lights, into microseconds, where cracks run through glass and spaghetti shatters in cascades, into nanoseconds, where molecules drift and the speed of light becomes a practical unit of length, into picoseconds, where molecules stop drifting and only vibrate, into femtoseconds, where electrons rearrange themselves into new chemical bonds and photosynthesis begins, into attoseconds, where electrons orbit within atoms, into zeptoseconds and yoctoseconds, where nuclear events happen and quarks and gluons behave in ways that have no macroscopic analogy. The pattern is not accidental. Going faster in time means going smaller in space. This is not just an observed correlation. It's a deep feature of physics. The processes that happen quickly are fast because they involve light objects, strong forces, or short distances. Electrons are light. Nuclear forces are strong. Nuclei are small. Chemistry happens at speeds set by the speed of electrons. Nuclear physics happens at speeds set by the speed of nuclear force propagation through nuclear-sized distances. Each layer of the timescale onion corresponds to a layer of physical reality nested inside the previous one. The journey inward through time is also a journey inward through matter. One thing worth asking, is there a bottom? Does time keep subdividing, or is there a smallest meaningful interval? There is a natural candidate, the Planck time, roughly 10 to the power of minus 44 seconds. It's derived from the three fundamental constants, the speed of light, the gravitational constant, and Planck's constant. Below the Planck time, the mathematics of quantum gravity, which we don't yet have, would have to take over. Below it, our current theories produce nonsense, which might mean they've broken down, or which might mean nothing physical happens below it. We don't know. The Planck time is 21 orders of magnitude smaller than the Femtosecond. We're nowhere close to it experimentally. Between the Femtosecond and the Planck time lies 21 orders of magnitude of unexplored territory, the same ratio as between a second and the age of the universe. An enormous space of time about which we know almost nothing, except that something must happen there. Because physics doesn't simply end at the Femtosecond scale, it continues. We just can't reach it yet. And maybe that's the most honest thing to say at the end of this journey. We descended as far as we could, and found the boundary not at some fundamental wall, but at the limit of current instruments. The history of physics at every scale has been, we built a tool that could see further, and we found something new. There is no particular reason to think this will stop. A second ago, you pressed play, and now you know what was inside it.